welcome to Ambiq's first AI learning series presentation. My name is Carlos Morales. I run AI for Ambiq. Very quickly, let's talk about the AI development data flow and toolchain. So starting, data scientists live on the left hand of this diagram, and every model and every data scientist works a little bit differently. But in general, you start from the data. You look at the data sets that you have or you can generate. You see the nature of that data. In human activity recognition's case, the nature of the data is what we call time series, meaning it varies over time. And it generally, you can consider it a one-dimensional time series data set. Although there are 6 dimensions that we're looking at, 3 accelerometers and 3 gyroscopes, you treat them as 1D. Looking at that data, the data scientists will start looking at neural network architectures that might help. Is it an RNN? Is it a CNN? Are you going to use convolutions? Do you use an autoencoder? So the kind of decisions that happen early on. But they're not final decisions. It's a development process. So you write a model, which is actually pretty simple. The model itself is simple. Getting the data in and out is a pain. But once you have that pipeline going, you can start playing with the model and seeing which one produces better accuracy or which ones don't work at all. Once you've iterated through that a few times, and that may mean you go back to your data set and modify that. So all those arrows mean, it's not a very directional process. You go to a step called hyperparameter optimization. Hyperparameters are settings for the model. Like maybe you decided that you don't know how many convolutional layers you need, and so you left that open as a parameter. And HPO will find the optimal number of convolutions by just running it a bunch of times automatically and seeing which ones are better. That's an optional step, and it really doesn't help for very simple models like what we run in the Apollo 4+ environment. Once you've done that, if you have a very large data set or data set that a model that takes a long time to train, like some of our audio and speech models, that's only then do you move over to training on the full data set. Before that, you're taking samples. And that's because training on the full data set might take many hours. And so if your iteration is twice a day, you're not going to develop very quickly. So you want your iteration to be like your tests, your kind of modifications to be every couple of hours at most. But there's still an arrow back. So maybe you decided that you're ready to train, and once you train on the full data set, it broke. Back to the drawing. So there's arrows everywhere. After you've done this a few times, you're ready to start thinking about how to get that model deployed, how to get it from the training environment to the deployment target that you're thinking about. And in our case, that will be an EVB with an Apollo 4+ on it. And so that has, the training environment has gigabytes of RAM and terabytes of storage. Your deployment has megabytes of RAM and storage. So you have to compress a model somehow. And some of the techniques we do is you quantize from 32-bit floating point weights and activations to 8-bit, for example, or 16-bit integers. That helps with compute and also helps with the storage, but it also may lose you some accuracy. When you quantize, some models lose accuracy. But there's other techniques like pruning, where you get, it's kind of, you watch the model as it's running, and you notice that some parts of the model aren't pulling their own weight, so to speak. It's pun not intended. So you get rid of those and see what happens. And if you don't lose too much accuracy, you leave them out of the model. So you can actually prune 80–90% of the model in some cases. And then finally, there's something called distillation, which is a really interesting technique where you have the big model and then you have a little student model. And you let the big model do its thing, and the student model is not training on the traditional way. It's watching the inputs and outputs of that model and trying to imitate them. And you can compress, you can combine all these techniques to produce a very compact, efficient model. When you've done that, the rest of the stuff is software engineering, right? So now you're getting into, up to now you were in the kind of the Python space. And now you're getting into the C space. And C is the stuff that's going to run on your target. So basically this consists of getting it into TensorFlow format, writing the TensorFlow kind of harness, like how do you load the model, and Rohan is going to show you a little bit about that, and then how you invoke it, how you get the data into the right shape and format that the model needs. And so this is more software engineering. Usually engineers live on one or the other side of this, but for AI, really, especially in this space, you need somebody who, like Rohan, has the full spectrum of skills. So Rohan is going to show you all he did everywhere from every step from the data set selection all the way through deployment and testing. Rohan's model is going to be part of our ModelZoo once we've hardened it and turned it into something that is more like a product. And a ModelZoo is basically a reference library, but us data scientists can't call anything what it really is. It sounds too normal. So it's a zoo of models, and basically every one of those models in the zoo has everything you need to recreate that locally. So it has all the scripts that you use for training. It has a pre-trained kind of model. The weights have already been calculated for you, so you can play with that. It has scripts for massaging and corralling the data sets. And then it has a lot of kind of artifacts that help you understand what's going on. So documentation, something called Jupyter notebooks, which are an easy way to run Python in a kind of a very visual way. And then, of course, a runtime that you can actually load to your Apollo 4 Plus and get running in it. It's important to note that these models, the models in the ModelZoo, are not production code. They're not intended to just cut and paste into your customers or into your environment. They're reference code. For example, the model that Rohan is going to show you was trained on a specific gyroscope accelerometer device sensor. You probably have something different on your devices, or your customers do. Or even if they have the same exact sensor, it'll be mounted differently, right? So they will have to do some work on their side to retrain and to adapt what we're showing them to their environment. But this gets you 90% of the way. And then it'll tell you what the missing 10% is. And so it'll be a big part of our solution. So, if you look at this screen, the top is documentation, guides, and so on. But the bottom is the reference architecture. So those boxes at the bottom are the zoo's components. They're citizens. Rohan is talking about activity classification, which is down there. But we have things like a speech enhancement coming, speech recognition, keyword detection, the OK computer everyone is familiar with, and so on. And so we'll be rolling those out over the next several weeks or months. It's important to understand why we're doing this. Why are we trying to run AI? Why are we trying to enable AI in the space? The truth is, it's twofold. One, you're surrounded by intelligent IoT today. I kid you not, I was at Costco, I saw a toothbrush that said AI enabled. So it's everywhere. Your watch has all these models. Your smartwatch or fitness band already has a human activity recognition model. So the first part of the answer is it's already there. So you have to be able to kind of enable that on your customers' platforms. The second part is that Apollo 4 Plus is an amazing hardware platform for AI. The non-volatile RAM, which is NRAM, is very, very well suited for doing AI. the amount of TCM, the tightly coupled memory, and SRAM that I have, coupled with the cache architecture, it just lets you do basically everything you want to. Then you throw in Spot, which is our sub-threshold optimization, and you can see the results here. When you compare CPU to CPU, we beat most of our competitors on standardized benchmarks by anywhere between 3 and 16x in terms of power efficiency. So without sacrificing any performance, any latency, we have a multifold performance improvement. Even when other chips have NPUs, neural network processing units, which accelerate the inference, we're still close. We're not too far off. If you look at the NDP 120, that's a very specific, that chip does one thing. But the other ones, they're close. And I zoom in over here. The critical thing to understand here is that this benchmark only measures inference. And real AI is not just the AI part. You need everything. You need this very low power sensor. You need low power processing to massage the sensor data. The little slice that's inference, it takes 10, 12 milliseconds. And then you need to do something with it. So having a low power solution across the board is critical to your customers. And AI is just a slice of it, but it's an important slice. And that's it. Rohan, I hope you're ready because I'm going to turn it over to you.
Sounds good. Yeah. Hey guys, I'm Rohan with the AI team, and as Carlos mentioned, I worked on the human activity recognition model. So without further ado, let's kind of get into some of the work that I did. All right. So let's actually take a step back and kind of discuss in more specifics what AI actually is. And I think a good way to describe it is a set of parameters like weights and biases that run against several examples of data, and it makes a prediction, and then from that prediction an error is generated, and the machine conversely updates its weights based on that error so that future predictions can be more spot on and the error is minimized. So that's AI in a gist. Now for the task that we kind of did, our goal was to use gyrometer data from a smartwatch to classify a person's movement to one of 5 groups that we list out here: sitting, standing, jogging, walking, and climbing stairs. And in order to do this, we obviously have to train a model to perform the classification and integrate an appropriate sensor so that we can get that data and run the model on it. And the first step in this process, as Carlos mentioned, was getting an appropriate data set to train the model on. Now, the data set that we used came from Fordham's Wisdom Lab, and it consisted of 50 users who performed each of the 5 tasks for 3 minutes. The subjects wore the smartwatch that had a 3-axis accelerometer and a gyroscope during the experiment, and the sensors generated readings at around a rate of 20 per second, yielding around 3,600 readings per user per task. And the way that we partitioned the data was that we allocated the data from 35 of the users to the training set. So that's the data set where the model is trained against and its weights are updated against. And then the remaining 15 were sent to the validation set, and that's what's used to kind of assess how the model is able to generalize on outside data. And the way we formatted it, the data, and the way we're passing it in as a single example is one example contains 200 time step chunks, which is around 10 seconds worth of data. And each chunk corresponds to a single person and a single activity. And if you look at the bottom there, we have a kind of an image of a sliding window. So what we did was we grabbed 200 time steps, slide the window over 20 time steps, and grab another 200 time steps. So it was that's how we partitioned it. And that yields a data set with dimensionality of the number of windows, however many. I believe it was 30,000 for our training set, and then the 200 time steps, and then within each time step there's 6 different channels, 3 for the accelerometer and then 3 for the gyroscope. And beyond this partitioning, we also did some transformations to add more complexity to the data set and make sure that it was set up in a way that we can optimize the performance of our model, the accuracy and the loss. One of the things that we did was normalizing each window. And we did that by kind of, for each of the 6 channels, we kind of went and got the mean, and then each value is the mean minus the value minus the mean divided by the standard deviation for each channel. And this helps the model better generalize when using data from other sensors than the ones that the dataset uses, Wisdom Lab used in their dataset. And then another thing that we did was time step permutation. So we got these 200 time step chunks, and we kind of just scrambled all the time steps up. And this is a method of data augmentation, and it basically adds more complexity to the data set so that the model can kind of, learn to see past noise and extract more valuable patterns within the data. And a good way to digest data augmentation is the picture on the left, which is a picture of a parakeet. So all of those 6 of those pictures are pictures of parakeets, but they have different levels of saturation. Um, so it's just basically extra noise, and the model, if it's trained correctly, can see past that and you know do a better job of generalizing when applied to outside data. As for the structure of our model, we included 4 convolutional layers, what are called convolutional layers. And to get a gist of what convolutional layers are, I think the the way it's set up in image, the way it's done in image recognition is a very good way to kind of understand it. So it's basically just a little kernel. If it's a 2D one, it's going to be an array. If it's a 1D convolution, it's just going to be um, well, it's going to be a matrix if it's a 2D convolution, and if it's a 1D convolution, it's just going to be a singular 1D array. And it kind of just goes over the image, does the dot, just kind of like goes through patches of the image or the example, and it kind of extracts features. Well, at least the way it's trained and the way the weights are updated, it's able to extract features. So in the case with the koala, it's able to like kind of figure out where the eyes are, where the nose is, where the ears are, and the hands and the legs. And then you kind of aggregate all those features together, and it helps, allow for better classification. Now it's harder to qualify such features with time series data of this sort, but it's kind of a similar idea. Um, so we have those 4D convolutional layers and sorry, 4 1D convolutional layers, and as you can see, each successive one has more and more filters. First one 16, then 32, 32, and then 128. The purpose of that is to kind of get higher level features towards the beginning of the network, and then as you get like go further down, you're able to get some of the more intricate features. Um, Also in the model, we have a couple of dropout layers. Basically, what those do is they turn off certain neurons in the previous layer, and that helps kind of prevent overfitting, which is when, you know, the model gets too attached to the data set and it learns the specific noise of the data set, and that's not something that you want if you want a model that's able to generalize to outside data. So the dropout layer kind of helps with that. It's a good analogy would be like you forget certain things when you're trying to perform a task because it's not necessarily important. Um, I think that's a good analogy and a good way to think about it. And some of our results after we train the model, if you take a look on the left, right here, you see a confusion matrix. The way to interpret this is the labels on the bottom, those are the predicted labels, and then on the vertical axis we have the true labels. So you want your values to be on this diagonal axis right here. So for all the walking predictions that we made, 1,577 of them were actually walking, but we still have some misclassifications as 198 of them were actually going up the stairs. So overall, not results were decent here. And then these 2 graphs are very important. This one is model loss, so basically the error the model has in making predictions, and this is kind of the behavior that you want. You want it to kind of flatten out here. And the reasoning for that is you don't want like a very steep kind of drop off towards the end, because that means like, oh, you haven't trained it enough and there's more training to be had. But here it shows that we've kind of maxed out the capability of reducing our loss function. And also you don't want this validation, this orange one right here, to start increasing, because that means you're starting to overfit and you're fitting to the specifics of the training set, which means that you won't be able to generalize to the validation set. So this is kind of what you want, like a flattened out kind of curve right here. And the model accuracy is kind of the same. You want it to kind of flatten out and make sure that the accuracy is not very steep towards the end, and that the test accuracy doesn't kind of decrease as you at a certain point. The next step in the development process was quantizing the model and deploying it on the Apollo 4 EBB. And the process of quantization involves, converting the 32-bit float weights to 8-bit integers, and that decreases the space significantly. And the obvious trade-off is that you're fitting the model in less memory, but that does affect the performance, as Carlos mentioned earlier. But in terms of our model, it didn't really have that much of a drop-off. When we ran the quantized model on our validation set, it was an 82.8% accuracy, which is only around 0.3% lower than the accuracy we were able to get on the unquantized model. Now here I kind of outlined the overall deployment process, which involves first quantizing, as I mentioned above. And then when you quantize it, there's a TF-lite file that you generate, TensorFlow Lite file that you generate, and you want to convert that to a .h file, which is a C file. And actually, if I can just illustrate it real quick, it looks like this. It's basically just an array of hexadecimal values that are meant to represent the internal parameters of the model that we're using. And then in your C code, this is the code that actually runs on the EVB. You want to just grab that model. Let me see where I grab it. Oh yeah, right here. You just grab it. The name is quantized har model TF Lite. That corresponds with this name right here. So you just grab that. And then you just allocate tensors, set everything up, and then you just invoke it down. You feed the sensor data. We gathered sensor data in another function, and then we just fed it into the model to the input tensor, and then we invoke it, and then we get the output tensor and kind of interpret which activity the model predicted it to be. So that's a good kind of overview of kind of how that process works. And then the next step that we kind of did was integrating a good sensor so we can get data to run the model on. And the sensor that we chose was the MPU 6050, and it contains a 3-axis gyroscope and a 3-axis accelerometer. So exactly the type of data that we needed. And we were able to program a I2C communication link between the Apollo 4 and the MPU, and also program the calibration process so we can ensure the maximal accuracy and precision in the data that we were receiving. And finally, just a note about how we kind of set up the sensor. We had the sensitivity of the sensor for the accelerometer sensitivity to be around 16 Gs, and the gyroscope sensitivity to be around 500 degrees per second. Right. There was still a persisting problem, however, when we were after we quantized and we integrated the sensor. The persisting problem being that the sensors are going to be different. The sensor in the Wisdom dataset and our sensor, the MPU 6050, are going to lead to different results. So how we kind of patched that up was collecting some data using the 650, and getting the pre-trained model and then running it for three or so epochs to kind of tune that out and see past the differences and help the model's ability to generalize to our sensor as well. And so far, the results we were able to get on live data, the model is able to consistently classify sitting, standing, and that should say walking, but it says jogging, but it should say walking correctly. But it has difficulty classifying when someone's going up the stairs or they're jogging. Some future priorities that we have with this model is integrating new data augmentation methods in the pre-processing stage, so we can get some more complexity with the data set, and even more improve the model's ability to generalize. Try out different model infrastructures like CNN LSTM or CNN GRU and figure out how to fit them on the EVB. CNN LSTM PM was one that I was heavily considering towards the beginning, but it is a little bit harder to fit on the EVB because I don't believe TensorFlow supports it to be quantized. And there's other approaches that we can try in our classification. One of them being a divide and conquer strategy, where we classify an activity as either static, meaning that there's no movement like sitting or standing, or dynamic, which involves walking, jogging, and going up the stairs. Basically any activity that has movement. So you classify it into one of those subgroups, and then within those subgroups, there's its own model where it's able to classify that within that subgroup. So it kind of splits everything up. So it's not, you know, 5 activities in one go. And finally, we want to obviously productize the example so the customer can better adjust the model to their own specs. Now, I thought it'd be a good idea to show you guys a good demo of how it works. So here we just want to calibrate it, lie the sensor flat until it's calibrated. The offset registers are set. And then the first activity I'm going to be performing is sitting. So there we go. Should run for about 10 seconds and then spit out a prediction. And there we go. We got a 96% chance of the prediction being sitting, and that is obviously correct because I'm sitting. So yeah, that's a quick overview of how that works. Obviously it's sometimes hard to emulate the environmental conditions necessary to get a good prediction, but that's the best we can do for now. And yeah, thank you guys for listening.
Thanks all for attending this quick learning series presentation. Please check in for more. There will be instructions for how to subscribe to our newsletter and be alerted to future presentations. Have a good day, and thanks for your attention. Thanks, Rohan.
Thank you, everybody.